Hey there, my name is Priyansh Nayak, and today I'll be demonstrating my final project for real-time rendering, which is my implementation of movement shadow maps in OpenGL. Without further ado, let's get right into it. Here I have my scene featuring multiple models, and I'm going to start by demonstrating my baseline, which is a hard depth shadow mapping system. This process has the light rendering a depth map, and each fragment simply compares the shadow space depth against the stored depth. This gives a very sharp and fairly binary shadow edge, as you can see, but also produces acne and self-shadowing along the actual mesh due to its raw computation and limitations. In order to resolve this, my immediate next step was the introduction of percentage close filtering, which uses the same depth shadow map, but instead of performing just one comparison, it samples a small neighborhood and averages the result, in my case, a 3x3 kernel. This allows softer shadows overall, but is fundamentally the same that comparison method. So even with the increment of the radius of the kernel, all it really does is just smoothens the edges but doesn't take away from all of its issues. This is where movement shadow maps come into play. Movement shadow maps have the process store four depth movements instead of just one singular depth value during the shadow pass, which allows a much better reconstruction process later on in lighting shader. This was my original implementation of moment shadow maps, which resulted in an overall better computation, which much more realistic shadows, but didn't entirely eliminate all the acne and existing issues, which is where I introduced improvements from the original 2015 paper as well as the 2017 paper for improvements. Some of these improvements are the use of a two-pass Gaussian blur filtering process in between the shadow pass and the light pass to allow for smoothing of the shadows, as you can see, which produces much more realistic results. Assign depth for much more clamped numerical computations and comparisons, as well as the introduction of a bias. This bias comes from the original paper, which allows us to calculate the computational depth to smoothen out all of this acne and produce much more realistic results. However, I felt that this movement bias on its own mostly just worked on deepening the shadows and then entirely remove all the acne, which is where this receiver bias comes into play. This is my own variable that effectively controls the amount of shell shadowing and light leaks. I found this to be a much more realistic way of handling how much you want to control the shadows and how much you want to have the depths be completed in a more natural fashion. As such, my entire implementation combines the methodologies of the original paper, uses my own improvements to produce more realistic results in the final paradigm. I'm going to acknowledge the fact that you see the frame drops over here, but that is primarily coming from OBS because it struggles to render OpenGL in the background. Here from my computational analysis in my report, you can see that movement shadow maps average about 60 FPS, which is a steep decline from the 160 in the baseline methods. However, trade-off is worthwhile due to the introduction of much more realistic results, as well as acknowledgement of several of the issues such as light leaks, self-shadowing, and the acne. That, in essence, is my entire project, and I hope you learned something new. Have a great day ahead.